Welcome back to the deep dive. We have quite the stack on the desk today. I'm seeing reports here from Continental UL Solutions, PlexityX, Code Intelligence, AU Movio.
It's a lot.
It really is.
Yeah.
And looking at it all together, it feels less like a reading list and, well, more like a survival guide for the next 3 years of automotive engineering.
That's a good way to put it, a survival guide. Because if you look at the dates on these documents, you've got the EU Cyber Resilience Act about to be enforced, the ASPICE 4.0 updates rolling in, massive shifts in validation strategies. This is, for all intents and purposes, the 2026 Technical Strategy Report for the entire industry.
Right. And we're not just looking at this academically today. We're going to simulate a high-level briefing. Imagine we're at a top-tier global consultancy.
Exactly. We're adopting that McKinsey-style top-down approach.
We need to be MEC.
Mutually exclusive, collectively exhaustive. Because our audience today isn't just the casual enthusiast. We are speaking directly to you if you're a chief technology officer, a quality director, a lead strategist at a major OEM, or a tier 1 supplier.
The very people who have to sign off on the architecture decisions that will define, what, the 2027 model year?
Pretty much. And the core question we are answering for them today is, well, it's simple, but it's also terrifying.
How do you build a car in 2026 without getting sued, fined, or just plain shut down?
And shut down might sound dramatic, right? But it's not. You just have to look at the casualty list that's already piling up.
This is the why, isn't it? The burning platform.
It is. The industry is facing a perfect storm. You have the software-defined vehicle, the SDV, which is finally hitting the metal. You have these aggressive new regulations coming online. And then there's the disruptive force of generative AI, which is just changing the very nature of how we write code.
And the stakes.
Yeah.
It couldn't be more real. I was looking through the notes on market impact. We have to talk about the Porsche Macan.
The Macan. And the VW Up, for that matter. These aren't niche models or some obscure prototypes.
No, the Macan is a cash cow for Porsche, a huge revenue generator.
It was. And yet, it was discontinued in the European Union, and you have to ask why. It wasn't because the engine failed emissions tests. It wasn't because customers stopped wanting it.
It was killed by UNES R155 and R156.
The cybersecurity standards. Purely and simply. The electrical architecture, the car's entire nervous system was just too old. It couldn't accept the new security measures required by law.
And a retrofit was just too expensive.
It would have cost more than the car was projected to make. So, from a business perspective, the only choice was to axe it. A perfectly good, popular car, gone.
That is the absolute nightmare scenario for any product manager out there. You have a product that people love, that people want to buy, but you literally cannot sell it because your compliance strategy failed years ago.
And that's the big takeaway. Compliance is no longer just a binder of paperwork you pull out for an auditor once a year. It's a market entry ticket, full stop. If your architecture isn't compliant from the ground up, you don't have a product. You have a museum piece.
Okay, so our mission today is to deliver a strategic roadmap to prevent exactly that from happening. We've synthesized all these sources, all these reports, into 3 core strategic pillars.
Right. Pillar 1 is what we're calling regulatory resilience. We're going to dive into how you can merge ISO 21434, ASPICE, and this big new one, the EU Cyber Resilience Act, into a single manageable system. The goal is to avoid drowning in endless separate audits.
Makes sense. Pillar 2.
Pillar 2 is validation evolution. This is the really deep technical part of our discussion. We need to explain why black box testing is, for all intents and purposes, dead, and why you absolutely need to move to something called instrumented fuzzing if you want any hope of passing an audit in 2026.
And finally, Pillar 3, the one everyone's talking about.
AI governance. How do we leverage generative AI for speed? Because we have to. There's no choice without completely breaking the chain of custody that safety standards like ASPICE demand.
Okay, that's a fantastic roadmap. Let's unpack this. Let's start with Pillar 1, the regulatory landscape. We're moving from just compliance to full-on strategy. And the big new monster in the room is the EU Cyber Resilience Act, the CRA.
The CRA is, it's a fundamental shift, and to really grasp why, you have to look at how we used to do things.
That's the old way.
The old way. We had automotive-specific standards, right? Like UN R155. Those were vertical. They were written by car people, for car people, very focused.
But the CRA is different.
Completely different. It's horizontal legislation. That's the key term. It applies to, and I'm quoting here, all products with digital elements.
All of them.
All of them. That means your smart toaster, your connected baby monitor, your network firewall, and yes, every single component in your vehicle that has a line of code.
So it captures everything that isn't explicitly carved out with an exemption.
Exactly. And it's designed to close the loopholes that existed in things like the Global Safety Regulation, the GSR. Think about the aftermarket, for example.
Oh, okay. Spare parts.
Spare parts, non-type approved components, all the things that used to slip through the cracks.
So if I was a Tier 2 supplier selling, say, a replacement sensor directly into the aftermarket, I might have flown under the radar before.
You might have, not anymore. If it has code and it's being sold in the EU, it's covered by the CRA, the scope is massive.
And the timeline is, let's just say it's not generous.
Not at all. It was passed in 2024. The first reporting obligations kick in September 2026. Full applicability is late 2027.
September 2026.
Mm-hmm.
I mean, in the automotive world where a development cycle is 3, 4, even 5 years, that's basically tomorrow morning.
It is. You are likely working on vehicles right now that will be subject to this, and if the architecture isn't ready, you're already behind.
And the penalties, they have real teeth.
Oh, they're designed to hurt. Up to 15 million euros or 2.5% of global turnover.
Whichever is higher.
Whichever is higher.
Right.
So for a major OEM, what does 2.5% of global turnover look like? It could be billions. This isn't a slap on the wrist. This is a board-level crisis.
Absolutely. But you were saying that the financial penalty, as terrifying as it is, isn't even the hardest part from an operational standpoint.
No, it's not. The hardest part is what I've started calling the impossible requirement. It's all about reporting speed.
I read this in the UL Solutions report, and I had to go back and read it again. The CRA demands an early warning of an actively exploited vulnerability within 24 hours.
24 hours. And then a full notification to the authorities within 72 hours.
Okay, let's just play that out. Let's make it real for a team listening to this.
Okay. It's Friday afternoon, 3 p.m. A junior developer, maybe just a year out of university, finds a bug. It looks a little weird. It could be a security vulnerability. They do the right thing. They log in Jira. Maybe they send a quick email to their manager.
And that manager is what, at a dentist appointment?
Yeah.
Or maybe they've already logged off for the weekend.
Exactly. So Monday morning rolls around. The manager gets in, sifts through their inbox, and sees the email at 10:00 a.m. They read it, realize it's serious, and forward it to the cybersecurity lead.
But the cyber lead is in an all-day workshop.
So by the time someone with the actual authority and expertise to assess the situation looks at this ticket, it might be Monday afternoon. You are already well past the 24-hour mark.
You've missed the deadline before you've even confirmed there's a problem.
You have. And you are now officially non-compliant. Now, compare that to ISO 21434, the current automotive standard.
Which is much vaguer.
It's a bit fuzzy. It says you need to communicate, but the timeline is more like as soon as is reasonable, the CRA says. 24 hours, no excuses. The clock starts ticking the moment anyone in your organization is aware of it.
So if I'm a CTO listening to this, my first thought is, my organization is not built for that kind of speed. We're too big, too siloed. What is the strategic solution here?
The solution, and this is where the insights from UL Solutions and Plexity X really come together, is the integrated PCMS. That's a product cybersecurity management system.
An integrated one.
The integration is the key. The problem right now in a lot of companies is audit exhaustion. Your engineering teams are just drowning. They have an ASPICE audit. Then a few months later, an ISO 21434 audit. Now you're telling them there's a whole separate audit for the CRA.
If you try to treat these as 3 distinct silos, you're going to fail. You just don't have the headcount.
You don't have the people or the time. It's impossible. So you have to map the overlap. You have to reuse evidence. And the tactical key to doing this, and this is where we get into the real nuts and bolts of execution, lies within ASPICE itself.
Okay.
Specifically, a process most of your teams are already using called SUP, P-9 Problem Resolution Management.
Okay, let's get specific on that. SUP.9 is just the standard process for handling bugs, right?
Yeah.
Tickets in a system. Every engineering organization on the planet uses some version of this.
Correct. You already have a ticketing system, Jira, Codebeamer, PTC, Integrity, whatever it is. The big mistake that companies make is they build a separate cybersecurity hotline. They create a new web portal or a special email address for security issues.
And what happens? Nobody uses it because it's outside their normal workflow.
Exactly. Engineers, like all of us, follow the path of least resistance. So the strategy is simple. Don't build a new tool, reconfigure the existing one.
So you take your standard Jira bug ticket,
and you add a couple of mandatory attributes, a simple drop-down menu. Is this a security vulnerability? Yes, no. Could this be actively exploited? Yes, no, and sure.
Okay, but I see a problem here. Most developers aren't security experts. If a junior dev clicks yes, just in case, does that automatically send an email to the European Union? Because that sounds like a recipe for disaster. You'd be spamming the regulator with false positives.
That's the common fear, and it's a valid one, but that's where the workflow automation comes in. It's the critical next step. You don't send it to the EU, you send it to your internal, your computer emergency response team.
So the trigger is internal first.
Internal only. When that yes box is checked, the automation in Jira immediately forks the ticket. It applies a specific tag, maybe a car candidate, and it triggers an alert, a real high-priority alert to the TARA team, the threat analysis and risk assessment experts.
And crucially, it timestamps it.
That is the most critical part. It digitally timestamps the precise moment of awareness. Even if the human manager is at the dentist, the system has recorded the event and notified the right people. You've started the clock officially, but you've also started the triage process immediately, in parallel.
So the 24-hour clock is ticking for you to verify if it's a real reportable issue.
Correct. But because you've skipped that whole manual email chain, you actually have most of those 24 hours to do the real engineering work, the analysis and verification. You automate the bureaucracy so your smartest people can focus on the actual problem.
That makes a ton of sense. You're embedding the compliance directly into the tools they're already using every single day.
It's the only way it works. And there's another massive implication of the CRA that we have to touch on here under Pillar 1, and that's the whole concept of end-of-life support.
The 5-year rule.
The 5-year rule. The CRA generally requires a support period of at least 5 years or the expected product lifetime. For a car, that can be much longer, but you have to maintain the ability to patch vulnerabilities for 5 years post-sale. This fundamentally changes how we have to treat the SBOM.
The software bill of materials, basically the list of ingredients for your software.
Exactly. In the past, the SBOM was a snapshot in time. You finished the car, you printed out the list of all the open source libraries and their versions, you handed that report to the release manager, and you moved on to the next project. It was a deliverable, you checked off a list.
Now you're saying the SBOM has to be a living document.
It has to be a dynamic, queryable database. You are now responsible for monitoring every single one of those components for post-development vulnerabilities for 5, 10, maybe 15 years.
So if a vulnerability is discovered today in a library you used 3 years ago, say, a specific version of OpenSSL,
you need to know instantly which ECUs and which vehicle models from which years contain that exact library. You can't spend weeks digging through old design documents and build archives.
you need to be able to run a query. Select star from fleet, where library equals OpenSSL version 3.0.
And if you can't get an answer to that query in seconds, you aren't compliant. You can't meet your obligations.
Wow. Okay, so the strategic takeaway for Pillar 1. Don't fight the CRA with a new department and more bureaucracy. Fight it with smart integration. Use ASPICE ACP.9 to automate that reporting trigger in your existing tools and transform your SBOM from a static report into a living, breathing database.
Precisely. Which brings us right into Pillar 2. So we have the process to report the bugs, but how do we find them before the hackers do? This takes us to validation evolution.
This is where we get deep into the tech. The reports all highlight this major shift away from things like static analysis and black box testing to something called instrumented fuzzing. So first, let's set the stage. What's wrong with the old way? Why isn't it working anymore?
The regulatory driver, again, comes from ISO 21434. It has this requirement that you must minimize unidentified weaknesses. That's a very broad statement, but for high-risk systems, what we call CAL3 or CAL4 in the standard, the traditional methods are just hitting a wall. They can't provide the evidence needed.
And by traditional methods, we're mainly talking about black box fuzzing, right?
Primarily, yes. Let's use an analogy to explain the difference, because it's really important. Imagine your ECU, your electronic control unit, is a locked room. Black box testing is like standing outside that room and just throwing random objects at the door, hoping to break it open.
You throw a rock, a shoe, a feather, a basketball.
Exactly. You're just hitting it with random data. You don't know what's happening inside the room. You can only see the result. Did the door open? Did the lock jam? Did smoke start coming out from under the door?
So it's effective for finding very obvious surface-level crashes.
Right. If the system is incredibly brittle, a well-aimed rock will break it. But in modern automotive software, the logic is so deep and complex, a critical vulnerability might only trigger if you perform a very specific sequence of actions. Like, you have to throw a rock, then wait exactly 5.3 seconds, then throw a feather, then knock on the door 3 times.
A very specific state machine sequence.
Right. A black box fuzzer is basically guessing. It's blind. The chances of it discovering that specific complex sequence purely by random chance are astronomically low, no matter how many millions of rocks you throw at the door.
Okay, so that's the problem. What, then, is instrumented fuzzing?
So this is the white box or gray box approach. This is the strategy being championed by companies like Continental and Code Intelligence. Instead of just standing outside the locked room, you put sensors inside the room before you start the test.
You're actually modifying the code itself before you test it.
Yes, that's the instrumentation part. During the compilation of the software, when you turn the human-readable C++ code into the binary that the chip runs, you insert these little probes. Technically, we call them sanitizers.
Things like address sanitizer ASAN or undefined behavior sanitizer UBSAN.
Those are the big ones. Think of these as tiny motion detectors or microphones that you install all over the code. So now, when the fuzzer throws an input at the system, it gets immediate, rich feedback.
It's not blind anymore.
Not at all. It doesn't just know, did it crash? It knows, that last input caused the code to execute lines 10 through 50, but it completely missed the important if statement at line 51.
So the fuzzer actually learns as it goes.
It creates a feedback loop. It's evolutionary. It says, okay, that input got me close. Let me mutate it slightly. I'll flip a bit here, change a byte there, and see if this new input can get me to hit line 51. It intelligently explores the entire map of the code. This is how you find those deep, hidden logical bugs, the memory leaks, the buffer overflows that sit 10 layers deep in the software stack.
And the report mentions a very specific metric here that is absolutely critical for the quality directors listening in: code coverage.
This is your audit defense. This is everything. ISO 21434, specifically requirement RQ 1011, asks for a rationale on your test coverage. If you're only using black box testing, you cannot definitively prove how much of the code you actually tested.
You can just say you threw a billion inputs at it.
Right. But for all you know, you might have just tested the same 5% of the code a billion times over and over again.
But with instrumented fuzzing, you have the data.
You have the hard mathematical proof. You can go to an auditor and say, we triggered 85.7% of all possible code paths. You can show them the branch coverage and the statement coverage reports. That is concrete evidence. That is what an auditor wants to see.
But I'm already seeing a potential bottleneck here: the hardware. If I have to run these millions and millions of tests on a physical ECU, a real box sitting on a bench in my lab, I only have so many benches.
And that is the scalability trap that so many companies fall into. Physical test benches, HILs, or hardware-in-the-loop systems, they are incredibly expensive. They can cost tens of thousands of euros each. They break down. You need people to maintain them. And you can't just clone them instantly. If you have 10 benches, you can only run 10 tests at a time.
And fuzzing needs millions, even billions of iterations to be effective.
Exactly. If you are relying solely on physical hardware, you will never, ever achieve the coverage you need in the time you have. This is where the strategy from Continental gets really smart. They are pushing everyone towards virtualization.
Breaking that dependency on the physical hardware.
Completely. They are using things called MCAL simulators. MCAL stands for Microcontroller Abstraction Layer. What this means, in simple terms, is that they simulate the chip's behavior in software. This allows them to run the actual AutoSAR software stack on a high-powered Linux server in a data center, not on a tiny automotive chip on a bench.
So instead of running one test on one physical ECU, I can spin up an Amazon AWS instance with, say, 96 cores and run 96 fuzzers in parallel.
Exactly that. You transform validation from a hardware limitation problem into a simple compute power problem. And compute power, especially in the cloud, is cheap, elastic, and massively scalable. This also enables the crucial concept of shift left.
Meaning you can start testing much earlier in the development process.
Much earlier. You can run these intensive fuzz tests at the unit level and the integration level way before the physical hardware has even been manufactured and delivered. A developer can literally run a fuzzer on their own laptop before they even commit their code to the main branch.
The report also mentions using this for testing things like secret diagnostics. This sounds like something out of a spy movie, but I gather it's a very real vulnerability.
Oh, it's one of the most common entry points for hackers. Developers often leave backdoors in the code for their own testing or debugging purposes. Things like, if I send this very specific weird-looking signal, unlock the system so I can debug it. Or, if I send this secret ID, dump the contents of the memory.
And of course, hackers love finding these.
It's their favorite way in. But these backdoors are often hard to find with normal testing because you need the exact key to unlock them. With virtualized, instrumented fuzzing, you can just hammer the diagnostic interfaces with billions of combinations at a speed and depth that physical hardware could never match. You can essentially brute force those secret backdoors and find them long before the car ever goes into production.
So the big strategic recommendation for Pillar 2 is stop relying solely on a final penetration test at the end of the project. It's too little too late. You need to deploy instrumented fuzzing directly into your CI/CD pipeline. Make it a quality gate.
That's the standard for 2026. A hard gate. If a new code commit causes the overall test coverage to drop below, say, 80%, the build fails automatically. No human intervention. It gets rejected. If you're not doing that, you're not really testing for security anymore. You're just hoping for the best.
Okay, that's a powerful and very clear directive. Let's move to Pillar 3. This is the one, as you said, everyone is talking about it at cocktail parties, but we need to ground it in engineering reality, the AI disruption.
Or, as we've framed it, innovation versus the stochastic trap.
Let's define that word for our audience, specifically in an engineering context. Stochastic.
It just means random, non-deterministic. And this is a huge problem because traditional automotive engineering, and especially a standard like ASPICE, is built on a foundation of determinism, absolute reproducibility.
If I input X, I must always get Y as an output.
Always. If I do on a Tuesday, I get Y. If my colleague does it next year on a different computer, they must also get Y. That's how we prove safety.
But generative AI, if I ask ChatGPT to write a requirement for a door lock function, and then I ask it again 10 minutes later,
You might get a slightly different wording. You might get a completely different technical approach. And that is what we call unstable evidence. In an ASPICE audit, unstable evidence is completely worthless. If you cannot reproduce your evidence, then in the eyes of the auditor, it didn't happen.
and yet the promise of AI is just too big to ignore. The Automovio report says it can reduce the effort for things like requirements engineering and basic coding by up to 50%. You can't leave that on the table.
You absolutely cannot. The insights from Automovio are critical here. You cannot ban AI. It is now the first-order design input for 2026 vehicle architectures. It's just too fast, too efficient. If your competitors are using it and you're not, you will lose on both cost and speed to market. It's that simple.
So the strategy isn't to ban it. It's to wrap it in a process, a chain of custody.
A verifiable chain of custody.
Explain that. How do you create a chain of custody for a ChatGPT prompt?
You have to fundamentally redefine what you consider to be an artifact. In the old days, the artifact was just the C code file or the Word document with the requirement. Now, the artifact is the combination of the prompt you use plus the input data you provided plus the model's configuration plus and a seed value.
The seed value. Okay, that sounds like the technical key here. That's how you tame the randomness, right?
That's exactly it. Most large language models, LLMs, allow you to set parameters like a seed value and a temperature setting, which controls the level of creativity or randomness. If you lock the seed and the temperature, you can force the model to be reproducible. You have to save that metadata alongside the output.
So if an auditor comes and asks, where did this block of code come from?
Mm,
You don't just say, oh, AI wrote it.
no. You say, it was generated by a model GC40, version 1.23, using this specific prompt, which is version controlled, with seed value 42 and a temperature of 0.1 on this exact date. That transforms the AI output from a random suggestion into a controlled, verifiable work product.
And then comes the next layer of governance, the human in the loop.
This is non-negotiable. The Automovio report outlines some very clear scenarios here, and I think this is a perfect framework for any company trying to define its internal AI policy. So, Scenario A, AI designs, and human reviews. This is the safe scenario. This is the recommended approach. The AI acts as the author or a co-pilot. It does the heavy lifting, it drafts the text, it writes the boilerplate code. But a qualified human engineer, a responsible person, as ASPICE defines them, must review, approve, and ultimately sign off on it. The human takes the final liability.
Okay, that makes sense. Then there's scenario B, a human designs and the AI reviews.
This one is classified as dangerous.
Why is that? On the surface, it sounds helpful, like having a digital assistant check your work for mistakes.
It's dangerous because of the risk of human psychology, laziness, confirmation bias, blind acceptance. If I write a piece of code and I ask the AI, is this secure? And the AI comes back and says, yes, it looks secure, I'm very likely to just accept that answer because that's what I want to hear.
But the AI could be hallucinating.
It could be hallucinating. It might have missed a critical nuance of your
Hmm.
specific hardware timing. It might not understand the full system context. You are outsourcing your own critical thinking to a statistical model, and that's a huge risk.
Which brings us to Scenario C, AI designs and AI reviews.
Forbidden. Absolutely forbidden. This is the closed-loop hallucination risk. If you have one AI write a requirement and a second AI write the test case to verify it, they might both agree on a complete fantasy that has no basis in physical reality. You've removed the human reality check from the process entirely.
So, for you listening, the strategy is clear. Use AI aggressively for drafting requirements in code to get that 50% speed boost. But you must mandate the human reviewer step, and you must digitally sign all AI-generated artifacts with the full metadata of the prompt, the model, and the seed.
And there's one more critical point on AI. The problem of hallucinations. AI is fantastic at structuring unstructured data. If you feed it a messy 50-page PDF of customer requirements and say, format this into proper IRB standard requirements, it's brilliant at that. But sometimes it will just invent an interface that doesn't exist.
It'll just make something up. Connect to the flux capacitor interface via the dilithium crystal bus.
Exactly. So your quality assurance process, which is ASIWay SUP.1, must be updated to explicitly include fact-checking steps for any and all AI-generated content. You have to have a human verify that the interfaces, the signals, the memory addresses it references actually exist in your defined architecture.
Yeah, we should probably mention that ASPICE 4.0 itself is starting to address this directly.
It is. There's a whole new process group called MLE Machine Learning Engineering. And one of the key requirements in there is the strict auditable separation of your training data versus your validation data.
The principle of independence.
Total independence. You cannot test your AI model on the same data you used to teach it. That's like giving a student the answer key before the final exam. They'll get 100%, but it proves nothing. You have to prove that your validation data set was kept in a sealed digital vault, completely separate from the training process.
Okay, this has been an incredibly dense and valuable breakdown of the three pillars. We've covered regulatory resilience with the PCMS, validation evolution with instrumented fuzzing, and AI governance with a chain of custody. Now, let's zoom out. Let's talk about the global market dynamics in part 4. Because the car's architecture itself is changing, and the entire geography of automotive power is shifting under our feet.
Absolutely. The big architectural shift, which is driven by physics and money, is the move from a domain architecture to a zonal one.
Why is this happening right now? What's the driver?
In a word, wait, the wiring harness, all the copper cables running through a car, is one of the heaviest and most expensive single components. I think it's the third heaviest part of the car, right after the chassis and the engine or battery pack.
And in a traditional domain architecture, if you have a component in the back of the car, like a taillight,
That wire has to go all the way from the back bumper to a central body controller that's usually sitting up front under the dashboard. That's meters and meters of heavy copper cable. Now, multiply that by hundreds, even thousands of signals in a modern car.
the weight and complexity must be massive.
It's insane. In a zonal architecture, that same taillight connects to a local zonal gateway that's located right there in the back of the car. And that gateway then sends the data over a single, lightweight, high-speed Ethernet cable to the central computer. The result is you can cut the wiring harness weight by up to 50%.
Which is absolutely huge for electric vehicles, where every kilogram you save translates directly into more range.
It's a game changer for EVs. But it creates a whole new challenge. These zonal controllers are now what we call smart switches. They're not just passing data, they're also managing power distribution. This radically complicates the hardware engineering, the HWE. You're not just blowing a physical fuse anymore, you are managing power distribution via software. You have electronic fuses, or e-fuses.
So the hardware is becoming software.
Everything is becoming software, which is the perfect segue to the geographic divide, the big one, China versus the West.
This is one of the starkest contrasts in all the reports we looked at. China is moving at a speed that is, frankly, frightening for traditional Western OEMs. Their average development cycle is now 18 to 24 months.
And in the West, what's the standard?
It's still 48 months, sometimes longer.
That's double. It's more than double. You simply cannot compete if your brand new product is already 2 years older than your competitors the day it hits the showroom floor.
So how are they doing it? Is it just a case of working harder or throwing more people at the problem?
It's more fundamental than that. It's a software-first mentality. It's a high degree of vertical integration. If they need a part from a supplier and it's not ready, they'll just design and build it themselves. And frankly, they accept a different risk profile. They're much more comfortable iterating on the car after it's been sold using over-the-air or OTA updates.
Meanwhile, Western OEMs are often burdened by their own legacy processes, the rigidity of the traditional V model.
The V model is fantastic for ensuring safety, but it is inherently slow and sequential. So the hybrid survival strategy that we're seeing emerge, and this is a key recommendation for you listening, is what we call pragmatic outsourcing.
Okay, break that down for us. Pragmatic outsourcing.
Western OEMs are finally realizing they can't build everything in-house and still move fast enough. So the strategy is to keep the core system integration and what we call the brand definition software in-house. That's the stuff the customer touches and feels, the user experience, the driving dynamics, the brand's unique signature.
But the other stuff.
You outsource the non-core software to specialized partners who are built for speed and agility. Let them handle the base layers, the drivers, the stuff the customer never sees, so your best people can focus on what makes your brand unique.
And at the same time, we're seeing Chinese companies building factories directly in Europe.
Yes, to bypass tariffs and meet the made in Europe requirements, you're seeing massive new factories from Chinese OEMs going up in places like Hungary. It's a very smart strategic move to neutralize the trade barriers.
So given all that, how does a Western engineering team actually compete with an 18-month cycle without just throwing their safety processes out the window? The report mentions adapting to something called Agile SPICE.
This is the necessary evolution. Traditional ASPICE can feel like a rigid waterfall process. You do all the requirements, then you do all the design, then all the coding. That model is just too slow for the modern market. Agile SPICE is about breaking that rigid sequence down.
Using agile methodologies like sprint.
Exactly. Instead of having one massive, terrifying joint review meeting at the very end of the project, you do smaller sprint reviews every 2 or 3 weeks. You're checking for compliance in small, manageable chunks continuously. And the other crucial piece is that you automate the documentation.
The days of manually writing 100-page Word documents for the ASPICE status assessor are over.
They have to be over. That is dead. In 2026, you generate your compliance reports and traceability matrices automatically, directly from your engineering tools, from Jira, from Codebeamer, from your requirements tool. The engineer does their work by filling out the ticket correctly, and the tool builds the document. If you have people manually writing reports, you have already lost the speed race.
This brings us to the outro. We've covered a massive amount of ground today. Let's try to summarize the entire strategic report for our listener, that CTO or quality director.
Okay, 3 core pillars to take back to your team on Monday morning. 1. Integration. Stop fighting the CRA and ISO 21434 as separate battles. Merge them into a single integrated PCMS. Use your existing ticketing system, your ASPICE SUP.9 process to automate that 24-hour warning trigger and get the triage process started instantly.
Pillar 2.
2. Technology. Stop relying on black box testing. It's blind and you can't prove coverage. You must adopt instrumented fuzzing combined with virtualization. You have to be able to see inside the code to prove it's safe, and you need to run it at scale in the cloud, not on a few scarce hardware benches in the lab.
And the third pillar.
3. Governance. Embrace AI, you have no choice but put a strong leash on it. Implement a chain of custody for all AI outputs. Remember the formula, prompt plus seed equals evidence. And always, always keep a qualified human in the loop as the final reviewer and signatory.
And I want to leave our listener with one final provocative thought. We've talked a lot about laws and tools and lines of code, but what is the actual underlying product that we're selling here in 2026?
That's a great question. The product is trust.
Explain that.
Think about it. In a world where generative AI can write functional code in a matter of seconds, software itself is becoming a commodity. Writing a C++ function to open a car door is getting cheap. Anyone can do it. But proving that that code is safe, proving that it won't be hacked, proving that it can't be tricked into opening at 100 miles per hour, that is expensive, that is rare.
That is the new premium.
So the entire value proposition is shifting from creation to verification.
Exactly. The winners of 2026 and beyond won't just be the companies with the fastest coders. They will be the ones who can prove to the regulator, to the customer, and ultimately to a court of law that their code does exactly what it is supposed to do and absolutely nothing else.
So compliance isn't just about avoiding a fine anymore. It's about building digital resilience. It's about having the proof that ensures your entire fleet of 5 million vehicles on the road doesn't turn into 5 million bricks because of a single hack you didn't catch in development.
The code is easy. The proof is hard. Focus on the proof. That is the mission. Take these pillars, go back to your engineering teams, and start the transformation now. The clock is ticking towards September 2026.
Good luck. You'll need it.
Thanks for listening to The Deep Dive. We'll see you next time.